Portugal, and I'm here to present a paper improving the prediction of functional outcome in ischemic stroke patients. As some of you might know, ischemic stroke is one of the leading causes of death and disability worldwide, especially amongst adults in developed countries. And 1/3 of the patients that survive still live with long-term disability. So any tools that can help the doctors in the decision-making process during treatment can really help a lot of people survive and not have to live with that disability. So to address this issue, the medical community has developed several scores, which we can see as rule-based classifiers. These scores are based on statistical analysis, but because they are meant to be calculated by doctors when the patient is admitted, they simplify the classifier, so they select a small set of features, they make the weights integer numbers. So for example, one example of this is if the patient is over 65 years old with some 1, if he displays a certain symptom with some 2, and then you do all this math, and if the score is above 10, you say the patient's going to have a poor outcome. So this is very helpful to be fast and in an emergency, but we feel that we can improve this by just using like a pure machine learning approach. And nowadays, it's not unimaginable to think that you can just input the information into a tablet or a computer and get that prediction without having to do it like yourself in your head. So because we didn't see any pure machine learning approach as far as we search, this is the proposal of our work. So we wish to predict the patient's functional outcome 3 months after the initial stroke event. We want to compare how our approach fares against what the medical community is already using. And we want to determine what performance gains can be attained when we include more features that are not obtained immediately when the patient is admitted, but are obtained during other stages of the treatment. So this is a small description of our data. We had 533 patients from the SITS thrombolysis registry, which is a worldwide registry that has, I think, over 20,000 patients, but we only had access to the cohort from the hospital we're working with. But so it can be reproduced by using patients from different hospitals, because the features are the same. So the features are collected when the patient is admitted to the hospital, which we call baseline, 2 hours, 24 hours, 7 days after admission, and when the patient is discharged. The features, they're not all the same, collected at different times. For instance, when the patient is admitted, you also collect demographic data like age, gender, risk factors, if the patient smokes or drinks. And then the 2 hours, 24 and 7 days, it's mostly medical exam results, the NYH stroke scale, which is a measure for the severity of the symptoms displayed. So we have quite a lot of different and rich features. So the first thing we need to do to make this a classification problem is to have like a target variable. The target variable is mostly used by doctors, and the one we chose is the modified ranking scale, which is a number between 0 and 6. That 0 is you have no symptoms at all, and 6 is the patient is diseased. And so usually the discretization is made if the number is smaller than 2, you say it's a good outcome. If it's bigger than 2, it's a poor outcome. And to measure performances, because we're not interested in accuracy itself, we're interested in the discriminative ability of the classifier. We looked at the ROC curves and the precision recall curves and the AUC, the area under the curve. We chose to use a logistic regression with L1 regularization. And the main reason for this is because since we're working with doctors, they want to be able to interpret the model. They want to be able to say this feature is important, this feature is not important, and logistic regression allows us to compare the relative weights to each other to give them these insights. Also, because we have L1 regularization, it performs automatic feature selection. Some of the weights will be set to 0, which further helps the doctors focus on which features are really important. And when we compared the performance of the logistic regression with other basic classifiers such as SVM or decision trees, we always had similar or better performance with SVM and always better with decision trees, but SVM is much more harder to interpret than logistic regression. Also, we didn't feel like we had enough data to justify the usage of neural networks and deep learning. We just overfit our data if we had such a complex model. In addition, we also always use for every experiment leave one out cross-validation, and we always perform the hyperparameter model search. This is our experimental design. So each of the 5 experiments, we just increased the number of features that are collected a long time. So the first experiment, it's the one that we compare with the scores because it only uses features that the doctors already are using when the patient is admitted. And then as time progresses, we include more and more of the features that are available. You can see that the number of patients is diminishing because we chose to leave out the patients that died between each of the experiments, not to skew our results. So on to results. This is the results for experiment 1 and the comparison of the logistic regression with the scores that doctors use. As you can see, it performs slightly better, but the scores are already quite good at what they do, as they are supposed. And we can see that the logistic regression already achieves an AUC of 0.8 almost, which is already quite good given the uncertainties of the problem. And looking at the precision recall curves, we can see that they're not very good. When we wish to have like a high recall, we have to compromise a lot of precision for each of these classifiers. So next we added the features that were collected for a long time. And we can see that the results improve significantly. So for the last 3 experiments, which include data collected at 24 hours, 7 days, and at discharge, we can see that the AUC is around 0.9, which is already a very good result. And we can see that this improves significantly on the scores that the doctors are using, and so we can be really sure about what's going to happen to the patient if we just let a little bit more time pass and use their information. Looking at the precision recall curves, we can see that they really improve a lot for the last 3 experiments, and we can have a really high recall without compromising any precision, like about 0.8, and we still have around 0.9 precision. And so we concluded that adding this more data can be very, very important to improve the prediction of ischemic stroke. Here I just have a small comparison between the classifiers. As you can see, even though a support vector machine performed better for the 2 experiments, it's very comparable to logistic regression. And since it's so difficult to interpret the support vectors and explain them to doctors, we really feel like logistic regression is the way to go. This concludes my presentation. If you have any questions, please.